This is section 2.3, one-step justifications. Now what we're going to do in this section is actually combine our learning from section 2.1 and 2.2. So we're going to take our if-then statements we've been working on, our conditional statements, and we are going to connect them to proof writing like we talked about in section 2.2, where we did proofs with algebra. So now we're going to do some proof steps with geometry. So to begin, why don't you go ahead and write the converse of the conditional statement that's listed right here. Let's go through this real quick. Remember that in our conditional, we can highlight our hypothesis with a specific color. I use red. So if a point divides or bisects a segment into two congruent segments, then that point is a midpoint. So pause the video, a little warm up, write the converse, and then if the converse is true, good to go. If it's false, provide a counterexample. Okay, so the converse you should have written is, if a point is a midpoint, then it divides or bisects a segment into two congruent segments. I apologize for my misspelling here. So if a point is a midpoint, then it divides or bisects the segment into two congruent segments. There's the G. All right, true or false? Well, if a point is a midpoint, then yeah, it divides the segment into two congruent segments. So that is indeed true, and we do not need to provide a counterexample then. So what we're going to see in this lesson a lot is that if we have a conditional statement that is true, and that its converse is also true, then we have what's called a biconditional statement, which means that, again, it works both ways, the conditional and the converse. That makes something a definition. If a conditional statement and its converse are both true, then it is actually helping us use or define the word that's being used in the if-then statement. So for example, midpoint. If a point is a midpoint, then it divides it into two congruent segments. If a point divides a segment into two congruent segments, then it's a midpoint. It works both ways. Therefore, we've really defined midpoint. It's a point that divides a segment into two congruent segments, whichever way we say it. So we're going to see a lot of definitions in this lesson, and we're going to use them to make one-step justifications. Okay, so what we need to be able to do in geometry proofs is we need to be able to take given information, like we talked about in that algebra proof writing lesson 2.2. We need to be able to take a statement and draw a new conclusion from it and have a reason for it, just like we did in the algebra ones. So here is our hypothesis, right? It says if point B is the midpoint of segment AC, then what do we know? Well, what we know is that if this right here is the midpoint of the segment, we know it breaks that into two congruent smaller segments. And then we can say that segment AB is congruent to segment BC. So that's what we're able to write. Segment AB is congruent to segment BC. That is the conclusion we can make from our given fact. Now, what is the reason that we are able to say that if point B is the midpoint of segment AC, that segment AB is congruent to BC? Well, because if a point is a midpoint, then it divides the segment into two congruent segments, which is what we reviewed on that previous screen. If a point is a midpoint, then it divides the segment into two congruent segments. That's the definition of midpoint. So that is our reason that we can say we can go from this fact to this fact. Again, if a conditional statement is true, you can use it to justify a step you are taking in your work. Okay, so next we're going to review or remind ourselves what complementary means. So we have a conditional statement. It says if two angles are complementary, then they add up to 90 degrees. All right, so for some practice, go ahead, write the converse. And there it is. If two angles add up to 90 degrees, then they are complementary. Again, this is a true conditional statement. If two angles add up to 90, they are indeed complementary angles. All right, so we can use that fact, that conditional statement, in a proof as well. So if we look down here at this example, we have two angles, and it says in our if statement, if angle 1 and angle 2 are complementary, then what do we know? Well, we just found out up here, right? If two angles are complementary, then they add up to 90 degrees. So we now know that angle 1 and angle 2 add up to 90 degrees because we know they're complementary. So we're going to write that. Again, here is our hypothesis, and the conclusion we can draw is, now be careful when you write this, we want to write the measure of angle 1 plus the measure of angle 2 equals 90 degrees. The measure of angle 1 plus the measure of angle 2 equals 90 degrees. If they're complementary, then we know that. And the reason for this is the conditional statement we just went over. If two angles are complementary, then they add up to 90 degrees. So there will be some pattern to our examples today. So here's another one. If a ray bisects an angle, then it divides the angle into two congruent angles. Let's again practice writing our converse. And for that, you should have got, if a ray divides an angle into two congruent angles, then it bisects the angle. Oh my goodness, another typo. I apologize. It bisects the angle. All right, so true or false? Well, if a ray divides an angle into two congruent angles, then it is bisecting the angle. That is, again, true. It's a biconditional, works both ways. So we can use it as a definition to write a conclusion in a step. So here we are again. Ray AB bisects angle CAD. So let's label our diagram here. I'm going to put a point on this ray and a point on this ray and a point on that ray. And I'm going to write my letters in there. So I know it's ray AB, and I know it's angle CAD. So I know this has to be point A for my angle. So we can put the C here and the D here. Practice drawing our geometry diagrams, and we can put our B here for ray AB. So if ray AB bisects angle CAD, we know that that means the angle is cut into two congruent pieces. So what pieces are those? Well, those are pieces CAB, angle CAB, and angle BAD. So this is our if statement, and we are going to write what we can conclude. Angle CAB is congruent to angle BAD. And the reason we are able to say that is the reason we just went over in the above conditional statement. If a ray bisects an angle, then it divides it into two congruent angles. So through those past few examples we've been doing, we know that if we have a true conditional statement, we can use that as a way to justify a step that we're taking. Another way to justify our steps is through the use of theorems. And we have a theorem we're going to read in just a second, but first let's remind ourselves what is true if we have a right angle. We know this. If an angle is a right angle, then what we know is that then it measures 90 degrees. Well, if you think about this a little bit, now this isn't a true proof of the theorem, but if you think about it, if we have angle A and I tell you it's a right angle, and then we have angle B and it's a right angle, then what do we know about those two angles? Well, we know that those two angles are congruent, because if this angle is 90 degrees and this angle is 90 degrees, they're both 90 degrees, then we know they're congruent because that's the definition of congruent. So through kind of a verbal proof there just now, this theorem is true. All right angles are congruent. If we wanted to write that in if-then form, we could. We could say if two angles are right angles, then they are congruent. Okay, so let's have some other if-then statements ready to use when we need to give reasons for steps. First of all, complementary angles. So if two angles are complementary, then what is true? Well, we already went over that one, right? Then their sum is 90 degrees. What if two angles are supplementary? What is true? Well, then their sum is 180 degrees. If you'd like to pause the video and see if you can fill in the last three on this screen before we go over them, you sure can. Next, a linear pair. If two angles form a linear pair, then what is true? Well, what is true, based on its definition, is that the angles are supplementary. So a linear pair's definition is that it forms a pair of supplementary angles on a straight angle. You might have said then they add up to 180, or their sum is 180 degrees, and that would have been fine too. Angle bisector. If a ray bisects an angle, then what do we know? Well, then we know the angle is divided into two congruent angles. An angle bisector is a lot like a midpoint. And lastly, vertical angles. If two angles are vertical, then what do we know about them? Well, you might know we already wrote this in our previous unit. We know then they are congruent. Remember, we set those equal to each other in unit 1B. Okay, so if you didn't pause in the previous example, I would really like you to pause the video right now. For each hypothesis, write the conclusion that you know, and then give the reason in if-then form. You are able to go from the hypothesis to the conclusion. Okay, so if angle 2 is a right angle, what do we know? Well, you should have written, because again, here's our hypothesis, angle 2 is a right angle. Then what do we know? Then we know the measure of angle 2 is 90 degrees. What's the reason in if-then form for that? Well, because if an angle is a right angle, then it measures 90 degrees. The next one, angle 3 and angle 4 are vertical angles. So then what did we know? Well, then we knew that angle 3 is congruent to angle 4. And that's with that if-then statement from the previous screen. If two angles are vertical angles, then they are congruent. And the last one, angle 3 and angle 4 are supplementary angles. So if they're supplementary to each other, we know they add up to 180 degrees. So measure of angle 3 plus the measure of angle 4 equals 180 degrees. And our reason for that one is, if two angles are supplementary, then their sum is 180 degrees. This is going to help us get started on writing proofs, going from a true statement or fact to something we can conclude because of that fact with a solid reason or piece of evidence.